Alright, the next problem we are going to work on is E9b.2a from section 9b, molecular orbitals. So suppose that a molecular orbital has the unnormalized form 0.145a plus 0.844b. Find a linear combination of the orbitals a and b that is orthogonal to this combination, and determine the normalization constants of both combinations using s equals 0.250. So we're given a molecular orbital, let's call it phi m, that is 0.145a plus 0.844b, where a and b are atomic orbitals. And we're given the overlap of the atomic orbitals s, written in direct notation, a, b is 0.250. Now we want to find a molecular orbital that is orthogonal to it. Let's call it phi m prime. And let's give it constants C1a plus C2b. Now the thing about orthogonal molecular orbitals is that their overlap has to be equal to 0. So I've written that in direct notation. Phi m prime equals 0. So to first we have to find the constants C1 and C2. So first of all, we plug phi m and phi m prime into that equation, and we end up getting 0.145 C1 AA plus 0.145 C2 AB plus 0.844 C1 BA plus 0.844 C2 BB. Now the overlap S is just, as given in the problem, is just AB or BA, which is 0.250. And since A and B are both atomic orbitals, the overlap with each other is just 1. So we substitute in AA, AB, BA, and BB into the equation, and we get 0.356 C1 plus 0.88025 C2 is 0, or C1 equals negative 2.473 C2. Now we can plug that into the equation for phi m prime. The C1 in terms of C2 to get negative 2.473 C2A plus C2B. Now since we are normalizing phi m prime anyways, we can just drop the C2 constant. And now we want to find the normalization constants of phi m and phi m prime. So let's write phi m and phi m prime in terms of a normalization constant. Phi m is nm 0.145a plus 0.844b, and phi m prime is nm prime times negative 2.473a plus b. So first, we want to normalize phi m. To normalize phi m, we need to set its inner product equal to 1. So to do that, we do nm squared 0.145a plus 0.844b, inner product with 0.145a plus 0.844b. And notice that we can take the nm out of the inner product to get an nm squared on the outside, which will make our calculation simpler. And we can expand that out into 0.145 squared AA plus 0.844 AB plus 0.145 AB plus 0.844 squared BB. And all that equals 1. What you end up getting is, after doing the math, is 0.795 nm squared equals 1. So you get nm equals 1.122. Similarly, we can do the same procedure for phi m prime, where we do the inner product of phi m prime with itself, which equals nm prime squared, negative 2.473 squared AA plus 2 times negative 2.473 times 1.00 times 0.25 plus 1.00 squared BB. Sorry, I meant to say AB with a 0.25. I got a little ahead of myself, but the reason why I can do that is because A, B, and B are symmetrical, so I condensed the middle term to make the calculation simpler. Now we can substitute 1.0 for AA, 0.25 for AB, and 1.0 for BB. And after doing the math, you'll get nm prime equals 0.412. Now, normalization constants are meaningless if the equation, if it's, well, what I'm trying to say is that the normalization constants here don't really matter because when we're trying to find the constants of the orthogonal with the orthogonal molecular orbital, the C2 we just set it equal to 1, but really it could be anything. So that's why the normalization constant doesn't really matter, and what really matters is the final answer. And after we plug in the normalization constant and multiplying it by the values of the molecular orbitals, we get phi m equals 0.163a plus 0.947b, and phi m prime, which is orthogonal to phi m, equal to negative 1.02a plus 0.412b, or the book gave 1.02a minus 0.412b. In this case, it doesn't really matter because both of those are orthogonal to phi m.